two proportion hypothesis test and examples. So in this video, we'll go through an example where we conduct an entire hypothesis test, so we do all the steps. Okay, this example, the intro is incredibly long, but I'm going to read it to you. So psychologists at the University of California, Berkeley were interested in studying whether people driving high-status cars behave differently than those driving other cars. State law requires that cars come to a complete halt and not enter a crosswalk that contains a pedestrian. So the researchers used an accomplice to step into a crosswalk on a busy street in California. The researchers took careful note of whether the driver illegally cut off the pedestrian accomplice by entering the crosswalk. They also rated the status of the car with a number between 1 and 5. A 1 meant low status and a 5 meant high. So high status would be like a really fancy, expensive car, and a low status would be a cheaper car. A vehicle was recorded only if there were no cars in front or behind it. So every time they recorded a vehicle, they waited until there was just like a single car in the area. This helped ensure that observations were independent. So what do I mean by that? Well, it helped show that if one car stops, a car behind it, so I guess the idea is that if one car stops, the car behind it might be more likely to stop, and so they wanted to avoid something like that, the first car influencing the second car. Although the actual study used an advanced statistical model to control for various confounding factors, we can perform a simple analysis of the situation to demonstrate how hypothesis testing for two proportion works. And we do this by combining the cars into two groups. And so we're going to group the low status cars, ones that were rated 1 and 2, and then we're going to group ones that are rated 3 or higher and call those high status. And so the researchers in this scenario, they observed 33 low status cars and 119 high status cars. Of the low status cars, 8 cars didn't stop, and of the high status cars, 45 didn't stop. So what are we going to do here? We're going to perform a 4-step hypothesis test to test the hypothesis that high-status cars are more likely to cut off a pedestrian. We're going to use a significance level of 0.10. Okay, now I had to cut off some of the description of this problem right here because it was just way too long, and then we wouldn't have been able to do any of the problem in the slides. So our step 1 of a hypothesis test is to hypothesize. In other words, we need to figure out what's the null hypothesis and what's the alternative hypothesis given the scenario described. Now, our null hypothesis is the neutral statement. It states, and I'm noticing a typo that I didn't catch earlier, sorry guys, that both groups of cars are the same. They cut off the cars at the same rate. Now, the alternative hypothesis is that the high status cars cut off pedestrians more often. How do we write this in math symbols? We write H0 is P1 equals P2. In fact, for these kinds of hypothesis tests, we always write this for the null hypothesis, so you never should even have to think very hard about it because it's always this. Now, how do we write the second one? It depends on which one's population 1 and which one's population 2. So for the alternative hypothesis, we're going to say that P1 is the proportion of all low status cars that would fail to stop if they were passing through a crosswalk when a pedestrian stepped into the crosswalk. And we're going to say P2 is the proportion of all high status cars that would fail to stop. And so we're told that we're testing whether or not high status cars fail to stop at a higher rate. In other words, we're testing if P2 is bigger than P1. And so we're using this inequality here. Okay, now that we've done step 1, we can do step 2. Now step 2 is to prepare. We have to state our significance level. We're told that it's 0.10. Remember, we use alpha for significance level. That's our symbol from earlier sections in chapter 8. And what else do we do? We need to check the conditions. We need to pick a test statistic that's appropriate for the scenario that we're described, and so we know that we're going to be using the 2 proportion test Z statistic that we've seen in previous videos. And then after we check the conditions, we'll be able to do step 3, but let's for now check the conditions. So the first condition is large samples. And so we need to have our sample sizes are large enough. Now, how do we do that? We compute these 2 formulas that you see here. And to do that, we need to know what a bunch of things are. In other words, we need to know what P hat is, the pooled sample proportion, and it's given by this formula. We need to know what N1 is, and N2 is to plug them into here. Now, N1 is 33. It's the number of low status cars that we observed because group 1 is the low status car group. Now N2 is 119 because that's the number of high status cars we had. It's the number of cars or people in this group. And then we also need to know number of successes in sample 1 to plug it in here and number of successes in sample 2. So we need to know all these things that are used to plug into the formulas. So number of successes in sample 1 is 8, we were told. That's number of people in low status cars that cut people off. And then number of successes in sample 2 is 45. That's number of people in high status cars that failed to stop or cut people off in the crosswalk. Okay, now we can compute all this stuff. So P hat is 8 plus 45 divided by 33 plus 119. So what I'm doing is taking everything on the right here and plugging it into this formula for P hat. Okay, so I'm going to save my P hat over here because we don't have enough room to do the rest if I don't get rid of what we were using. And we can calculate these two numbers in A and these two numbers in B. So how do we do that? For the first sample, we take N1 and we multiply it by P hat, where I'm getting N1 from right here and P hat from right here. And then we also multiply N1 times 1 minus P hat. So right now I'm doing both of these calculations in part A. And then we want these both to be bigger than 10, and if you plug them into the calculator, you in fact get both numbers are bigger than or equal to 10. We're going to do the same thing for sample 2, so we're going to calculate these two equations in part B. What do? We do N times P hat, and then N times 1 minus P hat. So those are right here. And if we actually type that into the calculator, we get both of those numbers are in fact bigger than 10, so we're good for condition 1. Quite a bit of computational stuff to check this first condition. Okay, condition satisfied, and we can move on to condition 2. Now condition 2 is that the samples are drawn randomly from the appropriate population. So in practice, this condition is hard to check. We've seen that, we talked about that in another video. Okay. Are the samples drawn randomly from their respective populations? Frankly, probably not. The problem here is that if you pick a random corner to watch cars at, you are sort of doing convenience sampling because at that specific corner, you might have, like certain people live in that neighborhood that might all share a quality, or you might be next to some kind of like place where people work where they all have a similar quality. And so probably we don't satisfy condition 2, but what we're going to do in this case is assume that it's satisfied and move on. Now condition 3, independent samples. The samples are independent of each other. This condition is violated if, for example, the same individuals are in both samples that we're comparing. Now, are the samples independent of each other? Yes, there's no reason to suppose the actions of low status cars will affect high status cars or the other way around. So we're going to assume that people are not getting in their low status car, driving around, and then going home and changing to their high status car and driving around, and then going through the same intersection where the scientists were watching this scenario. Okay. Now, condition 4, independent within samples. So are the observations within each sample independent? Yes, the researchers took care to make sure this was so by recording only cars that were not following other cars. So within each car observed, so for each car observed in this experiment, the researchers made sure that they were, not near any of the other cars, in fact, not near any other cars at all. Okay, so now that we've checked the conditions, we can finally do step 3. Step 3 is where we do our computational stuff. In particular, we find our test statistic. And so we've seen in another video that we can do this on StatCrunch by going stat, proportion stats, to sample with summary. And so before we do this, note that our alternative hypothesis was P1 is less than P2. So when we go to, when we get this box that pops up, we're going to want to select for the alternative hypothesis the less than symbol. Why is that? Well, notice if we go over here to this equation for alternative hypothesis, if we were to subtract P2 from both sides, we get P1 minus P2 is less than 0. So you get this equation here if you subtract P2 from both sides in our alternative hypothesis. Okay, so the rest of the boxes that you see here, we need to fill them in with number of successes, number of observations, number of successes, number of observations for samples 1 and 2. Now these numbers are 8 and 33, 45 and 119. 8 low status cars cut people off out of the 33 observed, 45 high status cars cut people off out of the 119 observed. Remember, you have to keep straight which one's population 1 and which one's population 2, so always write it down somewhere so you don't get mixed up and start flipping the 1 and 2. So we decided earlier that sample 1 was the low status cars and sample 2 was the high status cars. Okay, so let's go into StatCrunch and actually plug all this stuff in. So we go, this is from the last video, we go stat, proportion stats, to sample with summary. And we do 8, 33, 45, I think, and whatever that last number was, let's double check, 45 and 119. Okay, and then we don't have to ever change this one for what we're doing right now, but we need to change this box to less than. Okay, and then we're gonna push compute. So what happens here? We get all the stuff, and what are some things we're interested in? Well, the test statistic is negative 1.4476, and then we get a p-value, and our p-value is going to be of interest when we do our hypothesis test. So go back to our slides. We see that we get these two key numbers, so I've written them right here. Now, what do we do with this? We're going to try to make a decision. Before we do that, just so you guys have a better sense of what's going on, when we just did our calculation on StatCrunch, we didn't see any kind of normal curve, but theoretically what's happening here is our Z statistic, it shows us sort of like how far away P1 and P2 are from each other, or like what the likelihood is of them being certain distances apart. So Z-score of negative 1.45 is when P1 minus P2 is a negative number, where P1 is less than P2 by a Z-score of negative 1.45. Now the shaded area represents the probability that P1 minus P2 is even more extreme than negative 1.45 on the left, in the sense that more extreme where P1 is less than P2, but not bigger than it. If P1 was bigger than P2 by that amount, it would be like the stuff on the right. Okay, now what do we do in step 4? We interpret and we make a decision about how far away P1 and P2 are likely to be. So our p-value is less than our stated significance level of 0.10. So we decided in the beginning to have a significance level of 0.10. And so because this p-value is smaller than it, we reject the null hypothesis. What does that mean? We're going to conclude that the high status cars were more likely to cut off the pedestrians. Are more likely. Now, notice that we decided to have a significance level of 0.10 here instead of 0.05. If we had started with a significance level of 0.05, then our p-value would not be less than that, and we would not reject the null hypothesis. So keep that in mind. It's important that you know what your significance level is when you start out, and you always have to state it at the beginning. You can't just like change it around at the end, or else it's like not valid. So we started with this one, and so we have to go with it. Okay, one last note. Note that because this was an observational study, we can't conclude cause and effect, which means that we can't conclude that driving a high status car makes a person less concerned about pedestrians. Also, our sample was not randomly selected from a larger population, so perhaps the results would differ in different parts of the country. This was only conducted in Berkeley. The p-value was relatively high. If we had used a significance level of 0.05, we would not have rejected the null hypothesis. That's what we just chatted about. The original researchers used more sophisticated methods that enabled them to control for potential confounders and allowed them to see how the proportion of cutting off a pedestrian varied for each of the 5 status levels. So when they did these more refined techniques that are a bit more advanced than we're able to look at right now, they got a smaller p-value. So if you're worried about how we use significance level of 0.10 and maybe we should have used 0.05, they ended up getting an even smaller p-value when they controlled for various factors.